Yes, so I'm going to be the first of several people telling you something about the cosmic microwave background, or CMB. For some background, I've been working on it for basically my whole life, it seems like. And let's see, I do that. Okay, excellent. So yeah, I wanted to give you some context, which is that there have been 3 satellite missions to probe the cosmic microwave background, or CMB, and yet it's still relevant, and there are still a number of exciting pursuits that one can undertake using the CMB. And I should say, along with the 3 satellites, there's also been this history of several decades of measurements that were quite transformational from the ground and balloons, and many of them were led out of the Bay Area, as long as the Bay Area is expanded to include Santa Cruz itself. So we have some participants right here. All right, so luckily Phil already told you the whole standard model of the universe. I'll just give you this beginning with empirical features. So we know today from looking around at other galaxies and seeing that they're moving away from us, that the universe is expanding. We also know that it appears pretty isotropic on large scales, but it shows this huge dynamic range in density. And that huge dynamic range would be that empty space has only a few atoms per cubic meter, and black holes have much higher density than that. So the hypothesis that one can draw from that is that the universe is evolving from an even more homogeneous state, and that structures are forming from the action of gravity. And these maps of the CMB, they're mapping that original, much more homogeneous state. So let's see. Can I cue the CMB? Oh, how exciting. Yeah, so the CMB is quite it's one of the cornerstones of our understanding of this whole model of cosmology. And so this is an iconic graph that the Planck satellite team put together, where this is the sweep of time from left to right. And there are many interesting things to see in this plot. This is the time of superluminal expansion that Phil alluded to. And then there's this plasma. And then the CMB, as Phil described, is this leftover radiation from the plasma as it cooled off enough that it could no longer, the photons had an energy that was so low it could no longer re-ionize atoms if they occurred. And what's so great about the CMB at first glance is that it comes from a time when the universe was just much simpler, meaning the density perturbations were linear, not extremely huge. So there have been a series of, like I mentioned, 3 satellites, all of whom have made maps of the fluctuations in the CMB over the whole sky, which is usually shown in this mole-wide projection that makes the whole spherical surface look like an oval. And this plot is, as you see, plus or minus 300 microkelvin. The overall DC signal of the CMB has been removed. But you know, it appears kind of forgettable, and so in real space like this. And so we always prefer to look at it with the almighty power spectrum measurement. So we like to look at it in the equivalent of Fourier space on a sphere, where you expand in spherical harmonics. And then what's shown here is just the amplitude of the spherical harmonic coefficients squared. And it's typically written in units of temperature squared, as shown here. So what's great about this, and this kind of maybe takes you back to thinking about Shirley's talk, is that your eye as scientists, you just like look at that form and you're like, oh, I could probably fit that with 7 or 8 parameters, or 5 or 6 parameters. It's obvious, right? It's got these very clear features in it. You might not even have to use symbolic regression. And it turns out that, in fact, by thinking about the actual processes going on, one can understand why it has this form and fit it, and then derive cosmological parameters. This is a super wordy slide, but it's because I wasn't able to have my notes right in front of me, so I wanted to make sure that every point was made here, that gives you a sense of the craziness that is the CMB. So as Phil mentioned to you this morning, there's this concept that there was inflation, and it engenders these dark matter density fluctuations on superhorizon scales. So superhorizon means scales that appear to be farther apart from each other than the speed of light would have allowed, given how old the universe is. And that's because there was this early superluminal expansion period. That's why it can happen. And so as time goes on and the universe is expanding, it reveals these previously superhorizon like dimples in the space-time metric. And so you can, and there's this specific relationship that at a given time t star, there's a certain wavelength of fluctuation that can be revealed. Or we use k, which is like 1 over the wavelength. And so there's this tight relationship between t star and k star. And then, through a process that I'll say a teeny bit more about in a second, when this superhorizon, formerly superhorizon dimple is revealed, stuff starts happening. And what starts happening is this thing that we refer to as acoustic oscillations. So pretty much the gravitational interaction starts causing collapse of the baryons in the plasma into potential wells that already existed. And then that works too well, and so the plasma gets sucked into these potential wells, and then there's radiation pressure, because plasma has both baryons and photons in it. You get too many photons in there, and then there's radiation pressure that causes it all to come splashing back out again. And that turns out to be actually described pretty well by equations that look like a simple harmonic motion. But this is a plot versus wave vector on the x-axis, and yet it looks like simple harmonic motions that you would usually describe versus x. And the reason is because this relationship here relates, sorry, when I said x, I meant they look like simple harmonics motion where you plot x versus t. And the reason is because this point number 2, that I can't get back to. But point number 2 was, thank you, relating the x-axis multipole, or k, to time. And so that's why it has that great relationship. And then the expanding universe cools, and it congeals the plasma, and we get the CMB radiation being released to travel for something like 14 billion years, virtually unimpeded. All right, so another way of seeing it, even though I was kind of raining on the parade of doing visual stuff in real space, the second of the 3 satellites, WMAP, made this amazing plots in their paper where they took their entire map of the sky, and then they just stacked on all the blue spots, which turn out to be where there were overdensities of plasma. And when they do that, then this beautiful structure emerges, which all of you who think in Fourier space could have told me already, because you can only get structure in Fourier space if there was implicitly structure in the real space. And so this is showing what happens as those superhorizon dimples are revealed, which is that if you imagine being in that plasma right as the dimple is being revealed, then it turns out you're around 1.2 degrees away at that time. And so the plasma begins flowing in, and then when you get close enough, the sound speed starts mattering, then the radiation pressure effect happens, and the plasma begins flowing out, and you get these interference rings. So you get bright and then rarefied rings showing up like this. Okay, and it turns out that the whole kit and caboodle can be described. You can think of it as in terms of a transfer function. But there's a transfer function that needed, to understand something that has undergone a transfer function, you have to have some kind of guess or parameterization about what it looked like before all of that acoustic oscillation stuff happened. And so we usually, being astronomers at heart, just assume there was some kind of power law that described it, so that there's a power function in terms of whatever densities existed in the universe that had this form, where k is the is the wave vector. It's related to L. It's just that K is the 3D one. So that has two parameters in it, this coefficient A sub s, and then this exponent N of s. And then to parameterize the acoustic oscillations, you need to know the density of baryons, because they're the thing that's flowing in and out and being drawn by gravity. And then you need to know the density of the dark matter that was forming those deep wells. And then and that takes two parameters. And then there are some additional effects. You get rescattering due to reionization. There's the effect of the overall geometry of the space-time. And if you assume that it's flat, as we do, because we have some other evidence that that's not a terrible thing, then you are required to say that if it's flat, the thing that's making it flat today is dark energy. And that uses up two more parameters, and then you have 6 parameters, and that's like the vanilla ice cream model of the universe, because it's the standard model, and it's got, just 6 parameters in it. That's cool. But we all want to go beyond and find something, new and revolutionary, or as Phil pointed out, maybe understand a little more detail about those things that we call dark, like dark matter and dark energy. And so what's been done to date is kind of fitting 6 + 1 parameters to try to explore different things that occur to you might be interesting. So you can add extra parameters to the thing that you're fitting there and see whether that are motivated by your understanding of physics. So not quite what Shirley described as somewhat perhaps less pure, more physics motivated than what Shirley described. And you want to hear that side sound again? It just keeps on, our cup overflows. So what I was plotting before, those power spectra, I didn't mention it, but there were so many cool things I didn't say about it because I want to finish on time. But one of the aspects was that those power spectra cover a huge range on the y-axis, and they include both the sort of power spectrum of the intensity or temperature of the microwave background, but also effects related to polarization. And E and B are types of polarization, the linear polarization you can look for that will be described in more detail in the following talk. And TE is the fact that there might be cross-correlation between the intensity and the polarization. And the acoustic oscillations model that I described, it predicts these red, green, and black spectra here. And those are due to scalar, we call those scalar perturbations because the density fluctuations, density is a scalar property. But there's the possibility that gravitational waves might put a fingerprint on. And the talk after the break by Rito will discuss this, so I will just jump on. Oh, and Sean will touch on even cooler things or even earlier things that the CMB might be able to tell us about. All right, but I wanted to focus on what you can do, not from space missions, but how you might be able to compete with space missions, which usually are quite expensive, how you might be able to compete with those types of ideas by doing things on the ground using large telescopes. And here's the idea, here's the reason why it could be interesting, is because, sorry. It's very hard to go backwards. Thank you. So I was telling you about the patterns that we see when we look back through all of the stuff that's in the universe, and we look back at this early epoch when the universe was only around 14 billion years old, and we look at what the patterns look like there. But in fact, the CMB photons, they travel virtually unimpeded from that time to now, but not completely unimpeded. During this long sojourn through the universe to get to us, they are influenced by what's going on, and a lot is going on because all the structure that we see around us today is forming via gravitational collapse, and then later on via what astronomers like to call gastrophysics, I think, because it makes it sound like a ghastly, like complicated astrophysics, once you bring in E and M to compete with the gravity. And so if you have an instrument that has fine resolution, you can look for some of those fingerprints. Just to give you an example, one of the things that happens is the photons, they're confined to travel on geodesics, which means that if there are concentrations of matter on the pathway from the photon to us, then the photons will have to swerve around those gravitational concentrations. And that happens many times, like around 30 to 50 times for a typical photon on its way here. It swerves by of order an arc minute, which is not that small. And so by looking at correlations among photons that traveled in the same general vicinity of space, you can make a map of what all those gravitational concentrations look like, which is kind of amazing because you're mapping that entire stretch of space that's 14 billion years thick. So a little bit more on that. Yeah. So when you have huge maps of the CMB made with high angular resolution, which you can do from telescopes that are large, so you get high angular resolution, but on the ground, then you can do a number of things. So you can look more, you can make even better measurements of the primordial power spectra, so the initial conditions. And from that, when you get detail out at really high angular resolution, which corresponds to going right on the almighty power spectrum plots, you can look for traces that would be caused by having new light relics in the universe. So we know that we have light relics that are the neutrinos, but there might be even more than that. And you can understand more about the dynamics of the universe as characterized by Hubble's constant. And you can understand more about neutrino masses. You can understand the plain growth rate of structure itself, which tells you something about general relativity. And if you add in one other thing that can be done from the ground, which is you can make very special purpose telescopes that are highly shielded, and I believe that you will hear about that in some of the next talks, then you can also look for this signature from primordial gravitational waves. So just, I only have about 1 minute left, but I just wanted to give you a sense of how, for example, we can understand the dynamics of the universe. And so to do that, I'll show this plot of what we think is the deal about the energy density of different components that comprise the universe. As a function of, this axis is redshift, but it's proportional to 1 over the scale factor A, where the scale factor describes the way that the universe is expanding. And what happens is that, for example, matter, when the universe expands, its density just gets smaller by a factor of the scale factor cubed. For obvious reasons, it's like a number density. But radiation drops like the scale factor to the 4th power because for example, its black body spectrum gets stretched at the same time that it gets diluted. And then things like neutrinos, they're kind of in between because they start out being relativistic, but if they have some mass, at some point they start diluting more like regular matter. And so, and then dark energy, its crazy condition is that it has a constant energy density all of the time. And so from looking at the CMB, which is getting a snapshot of the universe in this particular position, and then comparing to what's going on today, if you understand the standard model, you think you would understand today just from looking at that early time. And just one of the things that's super wacky is if you just run those lines backwards and you say, this is what we have in the universe today. We have a whole bunch of dark energy, some dark matter, and a few baryons. If you go back and use the exact same colors over here, there was a lot, proportionally, there was a lot more dark matter, a lot more baryons. And the neutrinos and the photons, they really mattered. They were quite significant. All right, and it turns out that you can use the initial conditions to predict what Hubble's constants today might be, and when you do that, you don't get the same answer that people who look at supernovae get at, so that's quite interesting. If you want to build these CMB experiments, you need really great sites and really cool cutting-edge 100 millikelvin instrumentation. And that's all I'll say. That's just my end slide. But you should watch this space, and you should, in particular, watch the stage, because there'll be several cool talks coming up after the break. So thank you.